Hi, I'm doing the sample calculations for your spinach lab report, and you'll do some also. I'm getting these from the Pavia extractions PDF, which I uploaded for you, and it is it is a few pages out of this textbook by these authors, and the good stuff is on pages 701 and 702. This calculation shows how much solute you can extract by using a certain solvent and a certain volume of that solvent. So this math here shows K, a constant, which is the number of times, in this case 10 times, the number of times better solvent 2, in this case ether, is at capturing the solute than solvent 1. So in this case, in the textbook, they've got some organic molecules dissolved in water, which is solvent 1. And they're trying to capture those using ether, which is solvent 2. And they're using ether because ether is 10 times better than water. It is 10 times better than water at dissolving this stuff, this solute that they're interested in. Now, our situation is a little different. In your separatory funnel, in your separatory funnel, you had some petroleum ether in there. Here's your separatory funnel. And you put in there 12 milliliters of petroleum ether. I'll call that ROR as my abbreviation for ether. And you put also in there 14 milliliters of methanol, Me for the methyl group, OH for that OH group. And you also put in there 25 milliliters of water. 25 milliliters of H2O. You had your mortar and pestle with your spinach in there, and you put in here, you put about 5 milliliters of methanol, didn't you, to pour all of that spinach and its residue into the separatory funnel. Of course, you filtered this. Here's my little filter. How about that? My funnel. Okay, so you put that in the separatory funnel. Now, the organic stuff was supposed to be captured by ROR. It was supposed to first get captured by methanol, but see, methanol is polar because of this OH group. So methanol can dissolve the organic material and the polar organic material. So we don't want the polar organic material. We only want the nonpolar pigments. So for that reason, we used this petroleum ether, ROR. This is a nonpolar solvent. This is the organic solvent, which is mostly nonpolar. Then we use some more methanol here because this stuff is really good at dissolving polar organic things. It's better than water at dissolving polar organic things because it's got an organic part and it's got a polar part. Then we added water to remove all of those polar organic things because water is very good at dissolving methanol plus whatever was dissolved in the methanol. Okay, so let's get down to the math. Let's suppose that K is the constant that says how many times better water is at dissolving polar stuff, the polar impurities in the spinach extract, compared to the petroleum ether is. So let's say that water is 10 times better. Let's say that water is 10 times better. So this is water. Let's say that water is 10 times better than petroleum ether. Then this is petroleum ether at dissolving those polar impurities that we wanted to wash out of the ROR. So you ended up with two layers here. You had the organic phase and you had the aqueous phase, or the organic layer and the aqueous layer. The aqueous layer contains all the polar impurities and the methanol and the water, and the ROR contains just the nonpolar stuff and the petroleum ether. Now I know that we've got methanol in there, but I'm only showing water in the math. But I'm just showing the water to make this simple. We don't really know that the K is 10 for these polar impurities that remain in here in the organic phase. We don't even know what all those are. I mean, we can guess that there's DNA in there, there's some enzymes, some proteins from the plant, but we don't know how much of what molecules are there. So here I'm saying that water is 10 times more effective than petroleum ether at capturing the polar impurities. So we want to shake this up and get the polar impurities to be in the aqueous phase so that we can drain those off. Now, suppose that there were 10 milligrams of polar impurities, and water captures them all. Suppose that there are 10 milligrams of polar impurities and water captures all of those. Water doesn't capture all of them, so there's going to be some small amount of impurities left over in that petroleum ether after your first wash. Let's say that amount that's left over is X. X milligrams are left in the petroleum ether even after your first wash. So this is now going to be the concentration of polar impurities in the water. 10 milligrams, assuming that water captures them all, minus X. Realistically, X is the amount that water doesn't capture. So 10 minus X, that's the mass of the impurities. So if I want the concentration, then I divide this by the volume of water. Now, just for simplicity's sake, let me divide this by the volume of the total aqueous phase. In this case, the aqueous phase is 5 milliliters of methanol plus 14 milliliters of methanol plus 25 milliliters of water. So that's going to be 19 plus 25. That's 19 milliliters of methanol plus 25 milliliters of water. So that's 44 milliliters total. So that's this is the mass over 44 milliliters. Mass over volume is it can be used as a concentration, right? It's not only molar that can be concentration. It can be also mass over volume. Now here in the organic phase, in the ether, what's the concentration of organic impurities? Of polar impurities that are left in the ether after my water wash? Well, I assume that I captured all 10 milligrams of the polar impurities, and I left X milligrams behind. So I didn't capture all 10, but some X milligrams were left behind. So X milligrams is the mass of polar impurities in the ether after the water wash. So what's the concentration of polar impurities in the ether? Well, there are 12 milliliters of ether that you added there, so it's going to be 12 milliliters of volume there. So the concentration of polar impurities in the ether after the first water wash is X over 12 milliliters. Now, let me bring this 10 down, and let me bring this work down. So 10 equals 10 mg minus X divided by X. And this is divided by 44, and this is divided by 12. So I'm just going to say 44. I'm just going to say 12 milliliters up here and 44 milliliters down here. All right. You should work this math out for yourself. Having this as a denominator on top and this as a denominator on the bottom just means that if I want to put this in the numerator on top, well, I just have to multiply it instead of divide it. And this one, I have to multiply it instead of divide it. So now, let me just clean this up by getting rid of the units so I could just do my algebra. Okay, and now I'm gonna move this x over there, so I've got 10x equals 10 minus x times 12 over 44. But actually, I can move this 44 over there also. So I'll multiply both sides by 44, and I'll get 440x over here. So now 440x equals 10 minus, 10 minus x times 12. So that really means, this really means 120. So 12 times 10 is 120, and then 12 times x is 12x. So I can add 12 on both sides, so this is going to be 452x equals 120, and then x is going to equal 120 divided by 452. Let me get my calculator. 120 divided by 452, which is 0.27. So that's 0.27 milligrams of polar impurities. That's how many milligrams there are left in the petroleum ether. Now, I expect you to do this too. I don't expect you to do exactly what I've done, but I expect you to take this number here and do the second wash. Do the calculation, the imaginary calculation for the second wash, and show me your calculation. You can type it out, or you can do it on a piece of paper, take a picture with your phone, and then insert that photo into your sample calculation section of your lab report. If you do that, I recommend you use pen for the calculation because it comes out more clearly on the phone photo. But I want you to do the second wash in this way. Put this 0.27 milligrams right here instead of 10 milligrams. Instead of 10, it's going to be 0.27. And then solve for x the way I did. The x that you end up with, of course, is going to be much smaller than 0.27 milligrams. And that's not all. After that, I want you to, when you do this for the second wash, of course, in the second wash, it isn't 44 milliliters of water. It's 25 milliliters because you've already drained off the methanol or whatever methanol you could get to mix in with the water. All right, so that's the second wash calculation that I want you to do. And then I want you to get the x. Oops, sorry. I want you to get the x. Where's my x? Yes, I want you to get the x, which is going to be the total mass of polar impurities in this imaginary situation that you'll end up with after the second wash. And then I want you to do another imaginary situation. Start at the beginning. Over here, let's see, over here. Start at the beginning. And go back to the 10 milligrams of polar impurities. Go back to the 44 milliliters of water plus methanol. But instead of just 44 milliliters, add another 25 to that. You know what I mean? So use 69 milliliters of water plus methanol. Why? Because I want you to see the difference between using all 50 milliliters of water at once. So that would be 50 milliliters of water plus 19 milliliters of ethanol. That makes 69 milliliters of the aqueous layer total. I want you to see the difference between using that, see what X you get, and using two separate washes of 25 milliliters. Because there is a difference. One of these, even though in both situations you used the same amount of water, a total of 50 milliliters, in one of them you used those 50 milliliters in two separate washes, a 25 milliliter wash and another 25 milliliter wash. So I want you to see which one is more effective at washing out the polar impurities, which one ends up with a smaller X. Okay, so please show those two calculations, and that would be great for the sample calculation section. Thanks.